All right. Thanks. It's great to be here, and thanks. Is that good? Yeah. Okay. And thanks for that introduction. That was really kind. I don't think this is my bio sketch, but anyways, it was very nice. So let's see. This is an interesting classroom layout. I guess not everybody can see me, but oh hi! And I know a lot of familiar faces up here.
Pillars are using their X-ray vision.
Yes, well, it's a continuum ability, right? I mean, we can't see through pillars, but with better technology, we would be able to.
We're sort of disabled that way.
Exactly. Yeah, it's all relative. And I feel like I should have some activities for you to work on today, you know, because you're at tables, and but I don't. This is just going to be a kind of a boring lecture format. You can help me though by jumping in, interrupting me with questions, and I see lots of familiar faces actually from ME 112 this quarter, which is great. We have like an ME 112 satellite meeting right now. Oh, Healy too, everybody. Wow, this is great. Okay, so please do jump in and help me to make it a little interactive for you today. So, I'm Steve Collins. I'm a professor here at Stanford, and the goal of our group is to develop technology that improves mobility for people with disabilities like amputation or stroke, or people who have to walk under difficult circumstances like these aid workers in Africa. And it turns out that this problem is a lot harder than it might seem. People have been working at devices to address human mobility for hundreds of years, and there have been thousands of devices designed and tested that we know of, and almost all of them have failed to deliver a benefit to their user. And in recent years, we've had a few that have succeeded, and we've been starting to make some progress, but still most of the devices that have succeeded have provided a relatively modest improvement in performance. And the reason, I think, is that most of our efforts have been put forth by roboticists, mechanical engineers, that start with a presumption that they know what a device should do to help the person. And the real problem is we don't know what the person needs from their technology. People are really complicated in our bodies, our physiology, complex muscles, and complex dynamics of our movement, and especially in our nervous system. We're highly complex. The way we respond to and adapt to new mechanical environments or technologies. And so while our intuition is helpful to inspire us to try new things, and we have models of the body and the brain that are helpful also in guiding ideas for new technologies, they're insufficient to predict what will actually work. And this is something I have personal experience with. My PhD project to design a prosthetic foot to improve energy economy of walking was a failure. We made the device, it did what it was supposed to do robustly, we tested participants, and we found that it made walking harder after about 5 years of research by myself and my group. So, if this approach is not working, if our intuition and models are not predictive, then we need a new approach. And the direction that we've been working on over the past 8-9 years in my laboratory, and recently a few other laboratories, is based on a new approach in which we try to use an iterative process, an evolutionary process, to identify the functionality that people need from their device. And today I'm going to talk about 2 tools that enable that approach. The first are hardware experimental devices that we call universal device emulators, and these allow you to get to experiments on people fast. And the second are algorithms for what we call human-in-the-loop optimization, and these are intended to help you explore the vast set of possible assistance strategies more efficiently. This is a schematic of a typical emulator, It has large off-board motors and computers. Okay, so powerful off-board motors and computers that are tethered to lightweight and instrumented end effectors worn on the body. And the device will, it's sort of like a virtual reality device for your leg. It gives you the physical sensation of interacting with lots of different kinds of devices without the overhead of prototyping and building such a device. Keeping the motors and computers off board means you can have very powerful systems without having to worry about portability, packaging, and so on. And once you've designed those motors and computers, it's relatively easy to make new kinds of end effector to wear on your body. So you can make prosthetic limbs, exoskeletons of a wide variety to address different patient groups and needs. And for example, this is an ankle-foot prosthesis that has 2 independently controlled toes. And this allows us to control the torque and plantar flexion, which is when your toes are pushing down, which is thought to be important for powering gait and energetics of gait, and also inversion, eversion, which is where you shift your foot in and out like this, and that's thought to be important for balance during walking. And we use these devices to probe new ways of enhancing balance for amputees. Or more complex systems like this. This is a bilateral hip, knee, and ankle exoskeleton emulator worn by one of the designers, Gwen Bryan here, that we intend to use to develop ways of full lower limb assistance to make it easier to hike through challenging terrains like that with lower energy cost and improved speed. One of the things that I'm pretty excited about in recent years is that one of our former PhD students who worked on these projects started a company, Human Motion Technologies, or Humotech, and has started to sell these devices to other laboratories and to clinics. So we're hopeful that people with good ideas about what a robotic device should do, but without maybe the training to make such a system, can use one of these commercial tools and with a few lines of code have a device where they can test out some new innovative idea for improving human mobility. And they've been successful so far, selling about 10 or 15 systems to different laboratories. And in the long run, yes, yeah, please. No, yeah, please.
I have a question about how the purpose and use of exoskeletons that you're using are not different from commercially available exoskeletons that are described.
That's a great question. Okay, so what do people currently have? There aren't very many commercial devices that I would call an exoskeleton available. So there are a handful, like the Exo device, and you met Katie Strausser a few weeks ago, right? And I think their system is used in therapy, in hospitals, and I think there are a few hundred of those out in the world, right? It's been a little while since I talked with Katie, but the last time I talked, it was something like that. And I have colleagues down at, say, the San Diego State University who use the Exo system in their therapy. And my understanding is that there's some promising sounding early results that they may be an effective component of rehabilitation, but it's a little fuzzy still. And then there are some devices that are intended to assist people with complete spinal cord injury, like the ReWalk and a few other systems like that. So you have a person who's unable to walk at all, you give them a device like this, and then with the use of crutches to provide balance, your legs move through a walking motion and you can sort of walk. Then there's a huge gap, and on the other end we have orthotic devices that are passive, where you have some molded plastic that's created by orthotist or prosthetist to fit a person's leg. You take a plaster cast of the person's leg, make a positive, and lay up some carbon fiber or some just high-density polyethylene on it, and you have this sort of stiff sock that you strap onto your leg. And this can help with things like drop foot, which is you lose control of some of the musculature of your foot, and then you have this thing where you tend to drag your toe through, and this is bad. It makes it a lot harder to walk. You have to lift your foot quite a bit. Increases energy expenditure, decreases speed. So these kinds of devices are great for impairments like drop foot, but they don't restore mobility back to pre-injury levels. And we think that part of the reason is that they're passive. They aren't able to perform positive work. They're not able to perform the kind of control that the unaffected musculature and nervous system usually does. So we're operating in this space between sort of like a walking robot that connects to your legs and moves them through their motion, and on the other end, very basic prosthetic and exoskeletal or orthotic devices that provide some passive stabilization of the joint. And what we really want, the thing that makes it challenging is that you're trying to cooperate with the person. So the person and the robot their combined actions result in the movement of the person's body. And so the robot isn't dominating and the person isn't dominating, but their combined efforts result in this dynamic movement. And that's where the difficulty lies. And there are very few devices available. There's one commercially available prosthetic foot. That's the Biome there, which provides active powering. It's not yet Medicare reimbursable, so it's used by a pretty small number of people so far because it's quite expensive. And I think that's about it in this space. So that's in the 5-10 year kind of time frame. That's the space that we'd like to try to fill, to create these untethered devices that people can wear that are cooperating with them to improve their energy economy, their speed, and their balance. So people who can have some walking ability unassisted, and we can actually improve it. That's the idea. So there's a very long answer to a short question, but did that get to what you were thinking about? Okay. Thank you. All right, so let's see. We've got these emulators. They're commercializing. Oh, eventually we'd like to try to use these as part of a prescription regime as well. So you can imagine going into, you go into the eye doctor and you get that big thing, that big clunky thing, and they go better or worse, A or B. And you can do a similar procedure except with exoskeletons and prosthetic limbs. Some big clunky device that never leaves the lab, but it tells you what you need when you do leave the lab. And we'll talk a little bit about those untethered devices at the end of the talk. All right, so now we have this versatile hardware tool. How are we going to figure out what assistance strategies are best for an individual person? And here again, we're faced with that challenge that people are very complex. Each person is unique. And so actually what makes walking easier for me can make it harder for you. And we've seen this in our experiments. And people are constantly changing, especially when you're learning to use some new device. So we're trying to address all three of these problems with human-in-loop optimization. And the basic idea here is that you have a person interacting with a device, and while they're performing some task, like walking or running, you measure their performance online, feed that information to an optimizer, which then systematically varies device behavior. And this might seem pretty obvious, in the age of machine learning and AI and la-di-da and at Stanford here. But actually, almost no one's doing this. Nearly all development of this kind of device assumes that you have a good enough model of the person that you know what the device should do to get some change in performance. And so this loop is not closed. Now, this is also a hard problem. The things that we're trying to measure, like energy cost, that data is very noisy. It's slow to obtain. It takes a couple of minutes to get a single measurement. So we're not going to get data sets like you get from Virtual Turk with lots of, millions of coded images, that sort of thing, unfortunately. So it's quite challenging, especially the time-varying nature of the person's response. So this is something we've been struggling with for a few years, but we recently developed at least one approach that seems to work well. And this is an algorithm for improving the energy economy of walking while using an exoskeleton on your legs. So what we do is we have some device, it's programmed with some control law, a set of parameters that define the way that the device behaves. The person walks along while wearing it. We measure their energy costs. So this is a couple minutes of data, and we use a model to predict their steady state energy cost. Then we do that for several sets of control laws and use that to try to characterize the space, and then apply an algorithm that's called a covariance matrix adaptation evolution strategy. It's a little bit of jargon there, but CMAES, it's a commonly used optimization algorithm in the graphics community. You'll see it around if you ever get into optimization, to come up with a new estimate of the best parameter values and some new control laws to try. And then we feed those back to the person and keep going through this loop. So in a recent experiment, we used this to optimize control of an ankle exoskeleton worn on one ankle. And the torque was characterized by 4 parameters: the time that it turned on, the time that it peaked, and the value of the peak torque, and the time it turned off. And this is a small number of parameters, which makes our optimization a little easier, but it still spans a big space of possible device behaviors. We optimized assistance for 11 participants who walked on a treadmill at a typical speed of, if you're curious, people average 1.3 meters per second on a treadmill and about 1.5 meters per second over ground. If you want to stump someone with trivia later tonight. And we measured their energy consumption, and so on. We used one of our ankle exoskeleton emulators to apply the assistive torque. And the main result is that optimized assistance had this huge improvement in energy cost compared to what we've seen previously. About 25% reduction in the metabolic energy expended. That's the biochemical energy your body's using to perform a task like walking or moving around. And this is about 4 times better than the best result we'd seen with this system previously. And it's the largest improvement to date with a device on one ankle compared to devices worn at the hip, knee, and ankle on both legs. So it is clear that this was the human loop optimization approach was really effective at improving performance. Yes?
Did you find that there were sex differences in analyses?
We didn't collect a large enough sample size to try to answer that question. Usually the differences between responses based on gender are very small in this kind of study. People just aren't that different in how they walk among these kinds of populations with these kinds of tasks. Yeah. So there may be gender differences, but we would have to collect more data. And our sample size, we had about half men and half women in this study. We've since conducted lots of kind of similar protocols, and I have not seen anything, nothing noticeable. Yeah. So this caught our attention, right? We really have something here, we think. Looking at the optimized assistance patterns themselves, they varied a lot, and this might not look like much variation, but if you look at the timing of onset, for example, you would really notice this difference. This is about half the range of possible onset timings for these devices, and a fairly large range of peak torque across participants. And we know from follow-up studies that if you say take the optimized pattern for one person and feed it to apply it to another participant, you get a worse response. So we are actually getting a customized optimal assistance pattern for these people, and these subtle variations have a meaningful impact on performance. Yes.
Those variations, do they vary throughout a single person's walking pattern as well, or is it pretty constant for one person, but it varies from person to person?
It seems to be constant for a person, at least over the time scales we've tested. So this line would be every step, when your heel hits the ground, so you have no torque from the device, and then at around, so about 40% stride, so like maybe 200 milliseconds later, 0.2 of a second later, the torque starts, and it gets big, and then it drops down, and then your foot comes off the ground. And every step it will look like that. And for this other person, it will start a lot earlier, maybe 100 milliseconds in, and then it will ramp more slowly and then drop. So, but every step it'll look like that. And when we've tested people in some of our more recent protocols, we're testing people over the course of a few weeks. And we take the optimal assistance pattern from the first week, first day, and then apply it again after 5 more optimizations or something. And the optimized patterns from that day look similar to the original one, and you get a similar response. Yes, please.
Do you get the same kind of graph left and right leg?
We have not separately optimized left and right yet. So we.
If a person has a knee injury or ankle?
Well, we've begun testing individuals who've had a stroke, and the results are not as clean. And let me get to that in a minute. That's a good question. Yeah. Yes, please, Kevin.
Just to clarify, is optimization only for straight line walk?
Yes. Well, I'll show you. We've tried it in a few different steady patterns, but all steady gait. Yes. Well, yes. No like transient behavior standing. Then you ramp up to walk really fast for a few steps, then stop. And certainly that's something that's important before you put this into a product. So there's some fun studies out there about how people actually walk in the real world, and the most steps in your day, if you're a typical person, occur in long bouts of walking. So most of your steps will happen where you're walking for a few minutes relatively steadily. But most of your bouts of walking, so most of the times you start and then stop, are very short, just a few steps each time. So if you can't handle 5 steps bouts, you're in big trouble with these kinds of devices. However, we still are having trouble enough with steady gait, so we're going to address the transient stuff next. Our thoughts about how we will address it are to optimize for each sort of bin of behavior, and then use mode switching to identify when you're going from standing to different speeds, or transitioning between the speeds, which isn't too bad right now based on EMG and accelerometer data. Did that kind of make sense? Okay, yeah. Not yet. So that's something we're working on. So we've also been doing work in assisting running with similar results, and we're currently developing an untethered running exoskeleton. We think that we can, we have bold plans for it. The net improvement in energy economy over regular running shoes is about 10-15%. And if you add 1% energy cost to a person, they run 1% slower. And 2%, they run 2% slower. So if the opposite turns out to be true, then you might be able to allow a person to run 10 or 15% faster. And currently, the 2-hour marathon time difference is like 1%. You need a 1% reduction in your time to get below 2 hours. Just saying. That's a random thought. That has nothing to do with the other thoughts. Yes, please.
So when you look at data, do you first study the average walking speed of each individual and then have them walk at their typical walking speed, or do you have everyone walk at a walking speed?
It depends on the population. So for these individuals who had no impairments, we asked everybody to walk at the same speed, just to normalize it, because sometimes differences in personality lead to big differences in self-selected walking speed.
Could it be that maybe the difference in like the optimized step and how people step, could it be, for example, that difference is due to the fact that somebody is walking faster or slower than they normally do, and so by adapting their walking to that speed that's not usual for them, it's changing their stepping pattern?
It's possible, sure. So I imagine that if we perform this procedure for 1,000 people, and we took careful physiological measurements, like body segment lengths, how long is your tibia, how much of your leg muscle mass is in your soleus versus your gastrocnemius, etc. Maybe some baseline measurements of walking speed, that could be a factor. We might be able to predict these patterns from sufficient data. Maybe it's not 1,000, maybe it's 10,000, maybe it's 100,000 people, I don't know. Of course, when we're still in this laboratory phase, that type of data is way beyond what we can ever hope to have. So we're going to have to wait until we have commercial devices out in the real world. And then, as we've seen it with, say, activity monitors, you can then get these natural, rich, big data sets that can be interpreted to learn things about people's activity patterns and health and so on. Scott Delp, who's another professor here, had a nice study come out last year where they looked at how much people walk in different continents, for example. We're not doing great in North America, it turns out. Anyways, so my hope is that someday we'll have these devices that are optimizing online as people walk around in the world, and we'll have a little bit of information about people that we can then use to perform correlations or fancy correlations with machine learning.
So what I was thinking was whether the goal was to allow a person to complete a task in less hour, or for example, like for regular walking, how the person put in that same amount of power, but then like the assisted something to go faster. But then I realized like you could see it both ways. So like if they're walking at their normal rate and the device is assisting them, then they are going faster. So you are using like less power. So yeah.
Right on. Yeah, I think you're exactly right. Yeah. So along with disabilities that affect the lower limbs, you typically see both an increase in the energy cost to get a given distance and a decrease in self-selected speed and maximum speed to travel that distance, and also an increased likelihood of falling. So we'd like to try to address all three at the same time. We've mostly so far been focused on metabolic energy consumption because it is one number that is it's objective, it's unambiguously assessed. We have a mask that people wear, we measure the consumption of oxygen and carbon dioxide production in their bodies, and then use some ancient formulae to calculate something in joules, and then indisputably that is how much energy their body's using. For a self-selected speed, we're beginning to perform experiments where we try to improve self-selected speed, there's a little bit of psychology enters in a little more, right? Because you are choosing what speed you walk at. And there are all these funny ways that people perform these optimizations, and they interpret their own objectives and the experimenters' instructions in funny ways. For example, here's a sort of odd outcome. If you have a person walk from point A to point B, say it's like across a football field, and you give them a watch, and you tell them you have to arrive at point B at a certain time. If you pick a really slow time, people won't walk at a slow speed all the way and then arrive right at the time. They will walk at their comfortable speed and then stop and then walk a little bit more. If you go pick a fast speed, they will maybe run at their comfortable speed and then sprint to the end. And if you pick some weird intermediate speeds, they will like walk and then run and then walk and then run, and all these weird combinations thereof. So that's strange. Another one. Oh, I had a good second thing that I'm now losing here. Shoot. Okay. Well, it'll pop back in my head in a minute. Oh, yes. Experiment instruction. So, if I tell you to hop in place, however you like, just comfortably hop in place. People in North America, in the United States and Canada, where most of these experiments have done, for some reason it's not a global phenomenon of asking people to hop in place. Will hop about like this. They pick a frequency of about 2.2 hertz. And why? A very easy way to hop is this. Right? That's way easier than hopping steadily. And we don't tell people they have to do it a certain way. And they're actually, if you modify the frequency, you make it easier. But people interpret that what you want them to do is to hop. We know what hopping looks like, right? And a similar thing happens in walking self-selected speed experiments. So depending on what words you use, somebody can walk faster or slower. If you tell them, we're going to have you walk a certain distance, they walk faster than if you say, we're going to have you walk a certain time, because it finishes earlier if they go faster, right? So it's less clean than metabolic rate. And then finally, balance is the hardest, because falling is a really complicated phenomena. What causes a person to fall out in real life is a combination of their innate ability, the type of activity they choose to engage in, and the environment they find themselves in. So you might have very good balance under controlled circumstances, but live in a complicated, cluttered environment and fall a lot. You might feel confident about your balance and then engage in lots of kind of risky behavior and fall a lot, or the reverse. So in the laboratory, we have these pretty weak correlates to falling that we try to improve, but it's the least convincing of all the things. It's something that we care about a lot, but we have the least convincing data as to whether we've actually improved some of these balance. Another very long answer to a short question. Okay, but we've got lots of time. So, all right. So the patterns differed. Optimization discovered new things. It wasn't a simple thing that we could have predicted ahead of time, like torque was not maximized. It didn't match biological patterns of torque. Positive work input was not maximized, because we can pick patterns that result in more energy input into the person's body that doesn't result in less energy consumed by them. So there is something real happening here. We also tested this additional condition that we were calling the static condition, where we used a hand-tuned pattern of torque that was the best we'd seen in a previous experiment to get a baseline comparison. And two interesting things came out of that assessment. One is, okay, the optimal pattern was better than static, and we've confirmed this in other experiments, and we've seen larger improvements over static in other experiments. But we also saw that the static did pretty well in this optimization experiment. So these are data from the study I've been talking about. These are data from a separate experiment we performed with the same device and the same static pattern of assistance. And you can see that in that previous study we had a 6% improvement in energy economy. In this study we had a 19% improvement in energy economy. So what's the difference? Why do we see this change? We think that it has to do with the way participants are trained in this optimization protocol. For example, here's a participant walking with no exoskeleton in this clip. Now we have the exoskeleton on in zero torque mode, so it's not doing anything active, just added mass. This is when we first turn on the torque. And then this is after it's been optimized. Now if you're not accustomed to watching lots of people walk on treadmills, it might not be so obvious to you. But what I'd like you to watch for is the upper extremity movement in this clip. This person is quite uncomfortable with what that device is doing, and then here, very smooth and steady. And so when we started out on this project, we kind of thought the person will adapt quickly to whatever our device does, and that the most important process is going to be identifying what the device should do to help them. And what we found, both through observations like this and many failed attempts at optimizing, is that what happens on the human side of the system is at least as important and probably more important than the optimizations happening on the device side. So how we affect the person's learning of the device is maybe the most important component of why this was successful. So in our previous experiment, for example, we would give someone one setting and they'd use it for a long period of time. And that's how we would train them. And during this optimization procedure, you'd have one setting for a couple minutes and then some really different setting and then some other really different setting. And many of these were uncomfortable and difficult to walk with and not things that we would have picked to be assistive, right? But they forced the person to explore different ways of coordinating their own movements. And we think that pushed them into a more plastic state, a more malleable state where they were, when a good pattern of assistance came along, they were better able to exploit it. And again, this is something we've been, Katie Poggency has been leading a couple of experiments in our laboratory that suggest there is something kind of special about this, the patterns of torque that arise with CMA. That variation training is effective. All right. Just to see if we could do this in some other domains, we tried putting devices on both people's legs, and then we had them walk slowly, normally, fast, had them run, had them walk uphill and walk while carrying heavy load. And in each case, the optimized assistance pattern produced a big improvement in energy economy. In the case of slow walking for these participants, there was basically no effect, and what the optimizer did was reduced the torque to its lowest possible level. So it seems like even when the best thing to do was nothing, get out of the way, the optimization was able to discover it. And we also optimized a separate objective function, in this case minimize muscle activity in the assisted soleus muscle. And the optimizer found a pattern that reduced muscle activity substantially. As I mentioned, we're now trying this for other objective functions like self-selected speed and balance. Yes?
Amazing results. I guess the question I had is, what kind of populations?
Oh yes, these are all. These are students. These are people enrolled in this class, basically, right? So these are there's some cute tongue-in-cheek names for this patient group, or this population. But yes, these are all healthy young, fit 20 to 24-year-olds. So what happens when we try to apply it to populations with disabilities? And we've been working in two populations mainly. One is people with hemiparesis following stroke, and the other is people with amputation. And I'm mostly going to talk about stroke today. I'll just say about amputation, we've been having some of the similar challenges to what we've seen in the stroke population. So, oh yes, we just arrived on campus a couple of years ago, and so we got our lab about 6 months ago, which we were very excited about. And so these data are hot off the presses, and this is an ongoing thing. This is our build space. This is one of our gate collection spaces. This is an instrumented treadmill that's ground embedded, so we can measure interaction forces between the person and the floor. We have motion tracking cameras all around the room. We measure muscle activity with surface electrodes and metabolic rate, as I discussed previously. And boy, it would be fun to have you all come down to it'd be great to come down to the lab someday. Yeah. Well, if you'd like to, yeah, that would be fun. Yeah. Yes, you can have a lottery, and we can have one person try on the exoskeleton. We have 2 exoskeletons, so 2 winners to give it a try. And if you're up for it, you could stay a little longer and complete a whole protocol and get a little more data. Anyways, so here we have an individual with chronic stroke. So he had a stroke about 2 years ago, and his right limb is affected, so less able to voluntarily contract muscles, and a limping gait, an asymmetric gait, walks more slowly, has increased energy cost. And we're trying to assist the affected limb with our ankle exoskeleton and applying the same exact optimization procedure that we applied with the unimpaired population, as I described a minute ago. And what we've seen in our pilot tests is pretty modest improvements in energy economy. So we had these 25% improvements. That was great. We were excited among healthy college students. And then for our pilot tests among participants with stroke, we've seen much smaller improvements. And so we've been trying to figure out what's going on and come up with a better way forward. And there are a few possibilities. So one is that it's more difficult to learn a new motor skill when you have the impairments following stroke, right? So you're getting less information from the limb, and the descending commands have reduced quality, more noise. So it may just be that it's harder, it takes more time to learn how to coordinate the rest of the body with the device. And so we're thinking about different ways of giving people biofeedback and different training regimes to help them learn how to use the device better, and different devices that might be easier to learn how to use. So one thing that we particularly noticed with our participants with stroke so far is difficulty coordinating the affected knee and ankle. So when the exoskeleton pushes off hard, that ankle torque it will shove your knee backwards. So when you extend your ankle, that's sort of a moment on this segment. A joint moment is really, I've got 112 students in here, so if you do free body diagram, a moment about a joint isn't really, there's no joint for that. There's no free body that's a joint, right? So you have 2 segments. You have, say, the foot and the shank, and the foot gets a moment in one direction, and the shank gets a moment in the opposite direction. So if you're kind of making the foot rotate this way, well, you're making your shank rotate this way. And so what happens is we turn up the torque, and the knee pops backwards. And we trained a lot on this, and we give a lot of verbal coaching and instruction, but participants are having a hard time adjusting, say, the hamstrings and gastrocnemius activity to get more knee flexion torque at the time that the exoskeleton is assisting them. Yes, please.
During the occupation, detail of whoever uncomfortable walking, that could change the stride quite a bit. Like especially as you use your testing elderly coverage groups, like if you're worried about falling, or like how do you test their more extreme cases when like their stability is super high?
Yes, that's a great question. So first of all, we have participants wear a harness in case they fall. Yeah, so sorry, the question is maybe, are you saying perhaps instability is going to interfere with their ability to, yeah, absolutely. I think that's a really good idea. And especially in our work with participants with amputation, we are focusing right now strongly on ways of improving balance, because our approaches that try to, say, inject some energy through the device and reduce their metabolic rate have been pretty ineffective, but our approaches where we augment balance have worked. So we're thinking that a combination of balance plus propulsion assistance may work a lot better than just propulsion assistance. I think you're right. Yeah, and in our participants with amputation, we have a couple of different things we try. One is you look at the side-to-side position of the person's body and its velocity, and as you walk, you sort of sway side to side. And this is unstable, and it requires active control to stop yourself from falling over. Your front to back movements are actually more stable because you've got a leg there that just catches you when you transition. So as long as you can get your leg out in front of you, you kind of can't fall back forward or backward, or you're much more stable. Side to side, you have to kind of go out and then fall back just the right way. And if you go a little too far out, you're in big trouble. So we measure the side to side velocity and position, and then if you're not coming back this way as fast as expected, we push off more. And that increases your velocity in that direction. And this has proven quite effective, and we see, say, 10 to 15% improvements in energy economy for people with unilateral transtibial amputation. The other thing that people with amputation have a lot of difficulty with is uneven ground. So this is like always a number 2, number 3 complaint in surveys is I can't go to my kid's soccer game because it's in the field and I feel really uncomfortable walking on the dirt and in the grass. Or I want to go hunting, I can't go out into the forest because I feel really uncomfortable walking around there. And so we've been developing this, I think, pretty cool prosthesis control technique where when your foot gets close to the ground, we use your toes kind of like whiskers, your heel and toes. So they're sort of lightly spring-like, and then we sense that you start to get close to the ground, and then we measure the orientation of your foot relative to the ground, so we can kind of sense the shape, and then use that information to cancel out the shape of the ground. So it feels to you like you're walking on a nice flat surface, even with like 1-inch boards of wood that are dropped randomly on the treadmill. And that's something we're pretty excited about. Yes, Amar. 5 minutes, okay. Sorry, lots of side conversations.
So I'm good.
Yeah, good. Another thing we're trying is biofeedback, so giving people their ground reaction forces and asking them to try, okay, now push off harder with your affected limb and stuff like that. Okay, so I hopefully I've convinced you that this emulation technique and human loop optimization is a powerful approach that can be used to individualize assistance and help people learn how to use these types of devices. I think that the main challenge going forward, the best place we can improve the efficacy of these devices is in helping people learn how to use them. So careful studies of how people learn how to use these devices, and then develop new curricula that help people train to use the device more effectively, and perhaps close the loop and give a person the experience that they need given their current reaction to the device, to best learn how to maximize their performance with it, if that makes sense. It's kind of like in education, and we're actually working with some computer scientists who specialize in education. Emma Brunskill for NCS. You'll give people assessments and then see where they have a knowledge gap, and then give them training in that area. And perhaps we can do similar things, except with your physiological response to an assistive device. It's also hard to know what you're supposed to change, but that's another talk. Okay, so these are the folks who are responsible for all this work. JJ Zhang developed our human loop optimization approach. Kirby Vitta developed our exoskeleton hardware that we use in all these experiments. Tu Nguyen has been leading our stroke work, and Katie, Julia, Rachel, and Sung Moon have all been participating in various ways. And it's a very collaborative laboratory, and these projects require multiple people. Yes?
I wanted to ask if there's any opportunities for students to work in your lab, maybe over the summer or next quarter or something, maybe volunteer for as a subject.
Oh, yes. Well, so if there's opportunities to like be a research assistant, we have them sporadically, and I think in the spring and summer we may have, and we usually have a little symposium at the beginning of the quarter to match PhD students and their projects with people who are interested. We always are looking for volunteers. So if you want to come try on an exoskeleton, learn how to use it, and outperform what nature gave you, please come down and hang out with us for a little while. It's fun. Yeah.
Can someone with little prior knowledge also get involved with the lab, or would you recommend certain classes, like I'm assuming ME 112?
Oh, well, you don't have to take ME 112 to that's, although it's good. It's good. There is so much that we don't know about how to help people with these kinds of devices that everybody that comes into our lab, whatever their background, ends up learning a great deal of new stuff. So if we have mechanical engineers come in, they learn a lot about kinesiology, biomechanics, motor learning, and so on, and the complements of those statements. So, we expect people that join the lab will have a lot of training to do, and that's okay. Yeah, absolutely. Should we stop there? What do you say?
Yeah.
I have a whole other slide deck if you want to hear about unpowered exoskeletons. Okay. Great. Thank you, and thank you for great questions and discussion. That was awesome. All right. Thanks.
Please leave your forms on your desk. I'll pick them up.
Thanks, Dave. Good to see you.
No, it was great.
Hi. I feel like, have I seen you around before? Maybe? Okay.
My name is Jerry Jacobs. I'm a
Hi, Jerry.
fellow at CASBIS, the Center for Advanced Study.
Oh,
I'm a
right.
sociologist. I've been just
Okay.
kind enough to let me sit in on the class.
Right on.
Especially interested in exoskeletons. I'm interested in the elderly, and especially the elderly before they get too sick.
Yes.
So I'm interested in aging in place. And there's just a whole raft of new technologies that seem to me that are going to help people age in place.
Yes.
One way or another.
Yes.
Mobility and falling and
Yes.
stuff is absolutely front and center. I'm sure you know about this. So I'm really interested in, I can certainly understand why there's priority in helping disabled people who can't walk or have very limited functions. I'm not trying to say that that shouldn't be a
No.
priority, but there's this huge population
Yes.
of people who, haven't fallen yet, but they're gonna fall.
Yes. Yes.
And if they could be helped,
Right.
then-
Or are right on the edge of being able to get up and down the stairs, or whatever it is. Yeah.
Get the other folks a chance to talk. But,
No, absolutely.
But I'd like to talk about this a bit further.
Yeah. I'm interested in this. We're just starting to get into aging